All right, so today we're going to look at section 8.3, the second half of the section, which is on integrating with trig powers, specifically powers that involve secants and tangents. Before we get too into the examples, I want to remind you of an important identity that you learned about in pre-calculus. You probably saw it a little bit last year, but we haven't used it a whole lot. And that identity is 1 plus tangent squared equals secant squared. We're going to use this quite a bit with these problems. So let's take a look at some examples. Okay, we've started off here with the integral of tangent to the 6x times secant to the 4th x dx. What we're going to do, I want you to notice that secant is an even power. So what we're going to do here is we're going to pull a secant squared factor out of the secant. Make sure you see what I did. This secant to the 4th x, I just rewrote as secant squared x times secant squared x. And then I'm going to use an identity. Since secant squared x was equal to 1 plus tan squared, I'm going to replace this first secant squared x with 1 plus tan squared x. Make sure you see everything that's going on. Tan 6 hasn't changed. That secant squared x became 1 plus tan squared x. And then I still have the secant squared x sitting out there. Can you think of why we would need to save that secant squared x and why that would be useful to us at this point? Is there a u substitution we could make? If we let u equal tan x, the derivative is secant squared x, and that's what that secant squared x factor was for. Let's go ahead and make those replacements. And if we were to distribute and find the antiderivative here using power rules, we would simply get u to the 7th over 7 plus u to the 9th over 9. And then, of course, don't forget to change u back to tan x. And there's our antiderivative. Look at another one. Here we have the integral of tangent to the 5th theta times secant to the 7th theta d theta. Notice this time that secant was not an even power. So what we're going to do here is we're going to, since tangent is an odd power, what we're going to do is we're going to rewrite this by taking a secant power out of the secant to the 7th and by taking a tangent power out of the tan to the 5th. So now I have tan to the 4th times tangent and secant to the 6th times secant. Now think about if I could get both of these to be in terms of secant, that would work out nicely for a u substitution because the derivative of secant is secant tangent. So I'm going to use the identity we talked about earlier, and I'm going to replace tan squared with secant squared minus 1. Make sure you see this step. Tangent to the 4th is really tan squared squared. So I replace that tan squared with secant squared minus 1 from the identity. And then that whole thing is squared. So at this point, we can let u equal secant theta, and the du is the secant theta d theta term, secant theta tan theta d theta term that we have at the end. We do a little algebra on this and FOIL this u squared minus 1 out and distribute the u to the 6th. We end up with this expression. Take a minute and make sure you see that. And then just using power rules, my antiderivative becomes this. And of course, remember to replace u with secant theta. Okay, so let's sort of run through some tips or some general rules for working with these secant tangent powers. The first one is what we had in the first example. If secant is an even power, try splitting it up and saving a secant squared term and converting the rest to tangents. That will allow us to let u equal tangent, and the derivative is that secant squared term that we saved. If tangent is odd, this is what we saw in the last example. Save a secant and a tangent factor from both terms and convert the remaining factors to secants. That would allow us to do a u substitution with the secant. and have the secant tangent factor as the derivative. If there are no secants and tangent happens to be even, then try converting a tangent squared factor to a secant squared factor and expand it out. I think we have an example like that coming up soon. There are no tangents and secant is odd, try integration by parts, and we'll do one like that in a few minutes. And then as a last resort, if all else fails, you can try converting to sines and cosines. Some of these problems take a little bit of creativity, but the more practice you do, you'll see patterns and you'll pick up on some techniques you can use as you go along. Okay, let's look at an example with just an odd tangent power. So here we have the integral of tangent cubed x. So what I'm going to do here is I'm going to change this to tangent x times tan squared x. And then I'm going to use the identity for tan squared x and make that secant squared minus 1. And what I want you to observe here is that if we distribute the tangent and break it apart, we actually have two integrals we can calculate. Tangent is a formula we learned last year that you're supposed to have memorized, but if you don't remember it, check your integration list, and that's one of the ones we learned last year. The one here, the tangent x times secant squared x, think about what u substitution would be easy to do here. If we let u equal tangent x, the derivative is just secant squared x. So I'm going to rewrite that first integral as just u du. Of course, using a power rule, this first integral becomes u squared over 2. And then the integral of tangent x was the negative natural log of cosine x. So I replaced u with tangent x, and then this is the formula we learned last year. Okay, let's look at this example. We have the integral of secant to the fourth 3x times tangent cubed 3x. This looks complicated, but this is actually very similar to the very first example we did where we had an even secant power. So remember, if secant is an even power, let's split it up. Let's pull a secant squared factor to the outside. So my secant to the fourth 3x becomes secant squared 3x times secant squared 3x. And then let's replace secant squared 3x, the one in the front, with the identity to put it in terms of tangent. That becomes 1 plus tan squared 3x. And now if you'll notice, I have everything in terms of tangent except for the secant squared factor at the end. So we can do a u substitution and let u equal tangent 3x. The derivative then has that secant squared 3x term in it. Take a look and make sure you see what I did. I just pulled a factor of 1/3 to the front. So this integral becomes 1/3 times the integral of 1 plus u squared times u to the third du. And of course, if we distribute that u to the third, we get this. Using power rules and making replacements for u, here's your antiderivative. Distributing that 1/3 just to make it a little cleaner, we get this. Okay, let's look at this example. We have the integral of secant cubed x divided by the square root of secant x. Okay, I'm just going to rewrite this as secant x to the negative 1/2, just rewriting this radical. And what I want you to think about here is if we can get a secant x tan x factor in here, since tangent is odd, let's get a secant x tan x factor in here. I'm going to do a little algebra here to do this. Make sure you see what I'm doing with the exponents. I needed a secant x tan x here, so I pulled the tan x from the tan cubed. And to get the secant x, I wrote this term as secant x to the negative 3/2. Make sure you see that. Negative 3/2 plus 1 is equivalent to the negative 1/2 I started with using exponent properties. And then what can I replace tan squared with? Using the identity that tan squared x becomes secant squared x minus 1. And now we can let u equal secant x. And that takes care of the derivative, the secant x tan x we had at the end. This becomes u to the negative 3/2 times u squared minus 1, distributing the u to the negative 3/2, and then applying power rule and replacing u with secant x, we get this. Take a minute and make sure you see these last couple of steps. All right, in this example, all we have is an odd secant power. So this was that case 4 we had on the earlier slide. So when we have just an odd secant power, we're going to do integration by parts. So what I'm going to do here is I'm going to break this up into secant times secant squared. Now one of these is going to be u and one of these is going to be dv. To choose dv here, I would pick the one that's easier to integrate. I would rather integrate a secant squared x because we know the integral of that is tangent x. So I'm going to put the secant x in the u column and the secant squared x in the dv column. Taking the derivative of secant x, we get secant x tan x. Taking the integral of secant squared x, we get tan x. Remember when we talked about integration by parts, you want to stop when you get to something we can integrate. Well, this last row can now be integrated using some of our new techniques. Using the plus minus on the left side, I've got secant x tan x minus the integral of secant x tan squared x dx. I'm going to convert that tan squared x to secant squared x minus 1. I'm going to distribute the secant x and break that into two separate integrals. Now, think about what we have here. We have secant x tan x, that's taken care of. The integral of secant cubed x, I don't know, but I do know the integral of secant x. That's a formula we learned last year. That was the natural log of secant x plus tan x. That's one you're going to see quite a bit in this unit, so make sure you have that one memorized. And then I still have the integral of secant cubed x over here. Think about last year when we talked about integration by parts problems that were cyclic. The left side of this is the integral of secant cubed x. The right side of this is the integral of secant cubed x. So what can I do with that integral secant cubed x on the right side? Let's go ahead and bring it to the other side. So if we add this secant x cubed x integral to the other side, we get 2 times the integral of secant x cubed x. And of course, that's what I was trying to solve for in the first place, so I'm just going to divide everything through by 2. Okay, we have one last problem, and this is sort of that last case if nothing else applies. We have the integral of secant x over tan squared x dx. So let's go ahead and try converting these to sines and cosines. So the numerator was secant x, so we just have 1 over cosine x. The denominator was tan squared x. Notice I just rewrote that as cosine squared over sine squared and moved that to the numerator. Make sure you see that. So we're going to lose a cosine term, and I'm going to rewrite this. That's cosine x over sine x times 1 over sine x, which is this. Hopefully that looks familiar to you. That was one of the earlier integrals we learned last year. What's the integral of cotan x cosecant x? Negative cosecant x plus